It's time to talk about transformers. Transformers are probably the reason why we have AC electricity in this country. It enables us to change the voltage, to step it up to a really high voltage and step it down to a low voltage, which is really important for transmitting electricity over long distances. We'll talk about that later. But it also gives you a lot of flexibility. It enables you to plug in your neon beer sign into your outlet at home, even though it requires a very high voltage to light up those neon lights. And it enables you to plug in a device that requires a very small voltage that normally runs on a battery, like a laptop or a cell phone, and step the voltage down to the battery voltage so you can charge the battery or run the device from the wall. So let's take a look at how transformers work. This is a simple schematic of a transformer. It consists of an iron core. One side, we wrap a coil around the iron core, and on the other side, we wrap a coil around the iron core. But because there are a different number of turns, we can get some interesting effects. The primary is our input side. So we're inputting a voltage V1, and there are a certain number of turns on the primary coil. I'm going to call that N1. And the secondary is our output side. There are a certain number of turns on the secondary. I'll call that N2. And it would go to some kind of a device. Well, I'll just call it a load resistor. But if we measured the voltage over here with a multimeter, we would measure a different voltage. I'll call that V2. So on our input side, we're inputting voltage V1. On the output side, we're getting out V2. We have a certain number of turns on the input side, N1. We have a certain number of turns on the output side, N2. And if we're talking about current in that coil of wire, we could say there's a certain current on the input side and a certain current going through our load on the output side. Let's think about what's happening here. We have a changing magnetic flux through coil N1 because we're putting in an alternating current signal, right? An AC signal. Magnetic field increases inside that coil. The iron core directs that magnetic field through coil 2, the output side. The output coil says, wow, I've got a changing magnetic flux. I'm going to generate an EMF because I want to resist the change that I see here. And so we get an EMF generated. You can see that this would not work with DC electricity. There has to be changing current. There has to be changing magnetic fields. And that iron core just directs the magnetic field from one side through the other side. In actuality, they're not usually made like this. They're usually designed to look more like this. They have a center iron core, and the two coils are wrapped one right on top of the other one. So you get the maximum transmission of magnetic flux from one coil through the other coil. You can see here's an image of a transformer, and this center iron core is running right down the middle here. And our primary coil is right on top of our secondary coil. So you get maximum transmission of the magnetic flux generated by one coil through the other coil. Very little of that magnetic flux is lost. And because of that, these are very efficient. Now, an ideal transformer would be 100% efficient. All the energy from one coil would get transmitted through the other coil. In real life, they're pretty close. They're 90 to 99% efficient. So let's take a look at the power generated on the input side and delivered to the output side. The power on the input side, P1, is I times V, and the power on the output side is also I times V. If we have an ideal transformer, the power has to be equal because we have no energy lost. Everything we put in, all the power, all the energy we put on the input side, we get out on the output side. That's an ideal transformer. We know that they're not quite ideal, but they're pretty close in real life. Now, if we use Faraday's law of induction, that tells us that the voltage generated in that coil is N times d flux dt. And we also use that same expression for the secondary. And I've used the same flux for both. Why did I do that? Because I'm assuming this transformer is ideal. All the magnetic flux generated through one coil gets channeled through the other coil because of that iron core. That means if that's the same for both, then V1 over N1 has to equal V2 over N2. Or another way of saying it is our output voltage is equal to what we put in times this turns ratio, the number of turns on the secondary over the number of turns on the primary. So if there are more turns on the secondary coil, we get out a bigger voltage than we put in. And if there are fewer turns, we get out a smaller voltage. This would be called a step-up transformer if N2 is bigger than N1 and we're getting out a higher voltage than we're putting in. And it's called a step-down transformer if we're getting out a smaller voltage than we're putting in because the turns ratio is such that N1 is greater than N2. You might be wondering if we can just step voltage up and get extra energy that way. Why do we have an energy crisis? Well, we're not getting energy, we're getting more electric potential. Let's take a look at what happens to the current. The current has an exact opposite effect. If our voltage is going up because N2 is greater than N1, then our current goes down by that same ratio. And that makes sense because we already said, what do we know about this? The energy we put in is equal to the energy we get out. So if we step up the voltage to get a big voltage out, the current has to drop down because current times voltage is power. That has to be the same on both sides. Best case, it's the same on the input side and the output side. we know in the real world we actually get out a little less energy than we put in because of resistance in the wires and things like that. But best case, it's an ideal transformer. The energy in equals the energy out. And so if the voltage goes up, the current has to go down. This gives us a huge advantage in transmitting power from one place to another. Let's take a look at this simple example. We're transmitting power from the power plant to your house. What do we want to do to minimize the losses we have when we transmit power? We know we have some losses because the wires we use have resistance in them. So we make the wire the lowest resistance we can. We get that as low as possible. That's one thing that we do. But at some point, you're just not going to get the resistance of the wire any lower. You're going to have some resistance to that wire. Well, the house requires a certain amount of power. We have to get a certain amount of power to the house. And we can transmit that power a number of different ways. Power is I times delta V, I squared R, or delta V squared over R. So what this tells us is once we make the resistance as small as possible, delta V is the delta V from our power plant to our house where we're using the power. And we don't know what that is. So I'm going to focus on this center equation here. It tells me that for a given resistance, the smaller the I, the smaller the current, the less power is dissipated in that line. So I want the smallest current possible getting to my house. But I need a fixed amount of power at my house. So what do? I transmit at very high voltage, hundreds of thousands of volts. If I transmit at 500,000 volts, I can run a very small current. And then what do? I put a transformer on a line behind the house, on the power pole behind the house, and that transformer steps the voltage down to something that the house can handle, 200 volts or so. And then we send it in there. So we are transmitting from point A to point B. We're transmitting a very low current at very high voltage, because a very small current times a very high voltage gives us the same power as a big current and a small voltage. This enables us to transmit energy fairly long distances. We wouldn't be able to do that with DC power.